So let's say we have a cubic crystal that consists of 8 identical atoms. And as you can see, I'm not very good at drawing atoms that are absolutely identical. But let's say these are all atoms of iron. It really doesn't matter what element we choose for the purposes of this illustration. So those 8 atoms are connected into a cube-like shape. And let's say we have, we'll count the positions. So we'll call this position 1, 2, 3, and 4, and then 5, 6, 7, and then for that fellow that's back here, we'll call that position number 8. So we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 different positions. So let's say the iron atoms are all labeled. They're kind of like billiard balls. We'll call one, though, A, B, C, another D, and then E, and then F, and then G and H. So we've got 8 iron atoms, and they're all labeled with different letters. So what we're going to do is we're going to figure out how many arrangements for this cube. How many arrangements can we make if we take those 8 atoms and put them in this kind of cubic arrangement? Well, for that first slot, let's say we fill that first slot first, number 1. We have a choice of 8. We can pick any of those. Let's say we choose the letter H. So let's get rid of that guy. That's now gone. We have a choice of 8. Now there's 7 left. Let's say we choose C for the next one. A choice of 7, and we chose C. Right? So now C is gone. So we have 6 that are left to choose from. Let's say we choose the letter A. So how many are left? 1, 2, 3, 4, 5. We have 5 choices left. Let's say we choose the letter B. And as you can see, we can keep on going as we start filling in the letters. We have fewer and fewer choices for each slot. So let's say we put D over here, and then F, and then E, and then G. So now we've used up all the letters, and we had these many choices for each case. So this is one particular combination here, where we have H in the 1 spot, and then C in the 2 spot, and then A in the 3rd spot, etc. Right? So these are slots 1, 2, 3, 4, 5, 6, 7, 8. So those are the different spots, the different places in the crystal. But we had a larger number of choices when we started and fewer as we went through. So how many different ways can we combine 8 atoms into that cube? Well, it ends up that to get that number, we would simply take the product of all of these things. That's otherwise abbreviated as 8 factorial, and 8 factorial is equal to 40,320. So for this tiny little cube, there are 40,320 different configurations. That would be our value for omega in the Boltzmann's law formulation for calculating an entropy. And this is just one tiny little cube that would be utterly microscopic, well, below microscopic. This would be very difficult to image with anything but the most powerful scanning electron microscopes. So for something that is much larger, if you had a natural piece of halite that contains on the order of Avogadro's number, 10 to the 23 molecules, then this number really explodes to just impossibly large values. So we have many, many different kinds of configurations. So what that means is that the total entropy in a system can be very, very large. Total entropy can be very large. So when we say that in a spontaneous reaction that entropy increases, it isn't so much a hard and fast law, but rather something that is highly probable. This is the change that came with Boltzmann's equation. He started looking at chemical reactions not as things that were driven by immutable laws that can never be violated, but rather by highly probable systems. So that the reason that heat would flow down temperature from high temperature to low temperature is not because heat cannot flow in the other direction. It can, but it's just extraordinarily unlikely because of the numbers of configurations that are possible in these relative systems. So you can write that heat flow in a Boltzmann's law kind of formulation, and you'd be able to show that it's not necessarily impossible, but extraordinarily unlikely. I'm going to end here with just kind of a simple example of what entropy means from a Boltzmann's probability perspective. Let's say you've got a coffee cup. So here is a coffee cup that's sitting on some table in your home or office. So there's a coffee cup sitting on the table. So when I was a kid, I had a friend of mine who said that he was sitting next to his nightstand and a cup moved from the table off to the table and it spilled on the floor. And it happened without any external force. Well, of course, I did not believe him. It doesn't make any sense that a coffee cup could move without any external force. Maybe there was an earthquake and he just didn't notice it. Maybe he bumped the table or a cat moved by, who knows. Well, Boltzmann's law actually allows for another possibility. So if you think about all of the atoms that are in this coffee cup, it's going to be much larger than 10 to the 23 for any normal coffee cup, right? There are going to be many, many atoms, many times Avogadro's numbers of atoms inside this cup. There are a total number of configurations in that cup that would be related to the vibration. So if you look at the atoms that are in the cup, you can think of them as vibrating in various directions. There's a very small possibility that the atoms in the ceramic material that makes up this cup, maybe half of them at some arbitrary point in time would all vibrate in a single direction. Now that's extremely unlikely because they're all vibrating in random directions. But if they were to all vibrate, or not even all of them, if just half of them, or maybe a third of them, were to vibrate in one direction at the same time, then that cup could actually move without any external force acting on it. It's an amazing result, and it's also an incredibly unlikely result. So if anybody tells you that coffee cups are sliding around their tables without any external force, you can't necessarily say that it's utterly impossible, but you could say that it's so improbable that it is effectively impossible. So it's one of the strange but sort of interesting aspects of entropy. So that concludes our brief summary in this section.